Hello, everyone. So last time we were looking at graph sketching problems, and we were looking at the steps about how to sketch a graph of a given function by analyzing it and using derivatives. So last time, graph sketching. So in particular, we looked at polynomials and rational functions with oblique asymptotes, and also root functions. So we did a few examples of each type. There are still more types that we can consider, for example, trigonometric functions or exponential and logarithmic functions. So let me do a few more examples from these types. Some more examples. Sketch the graph of y equals f of x equals sine 2x. So how can we sketch the graph of sine 2x? Let's say sketch a graph of this on, let's specify the domain. This is 0 to 2 pi. Okay, so the domain here is already given. And if I said, if I want to find x and y intercepts, if I said x equals 0, then y will be equal to 0, which means the graph passes through origin. And therefore origin will be both x and y intercepts. So basically, let me say y-intercept, because for x-intercept, we have more points. There are more points where the graph crosses x-axis. So let's say if you want to have y equals 0, then that means sine 2x has to be 0, and then that means 2x can be 0 or pi or 2 pi or 3 pi or 4 pi, and therefore x will be 0 or pi over 2 pi, 3 pi over 2, and 2 pi. So these are the values for which sine 2x becomes 0. Y value becomes 0 at these x values. So here's the domain, x-intercept, y-intercept. We have more than one x-intercept. X-intercept means roots, right? So these are x-intercepts or roots. Okay. And then how about asymptotes? Well, asymptotes, we don't have any. Because remember, for vertical asymptotes, we need to see whether we have denominator or no, whether the limit of a function can be infinity, either because of denominator or because of logarithm, right? The limit should be infinity, limit of the function. But sign of a number is always between -1 and 1. It cannot go to infinity or minus infinity. So we don't have any vertical asymptotes. And horizontal asymptotes, of course, we don't have any either, because the domain is 0 to 2 pi, right? So for horizontal asymptote, you need to let x go to infinity, or you need to let x go to minus infinity. And again, we are not, x is not allowed to go to infinity or minus infinity, because x has to be in domain. Domain is 0 to 2 pi here. So we don't have any asymptotes. Now let's see whether we have any critical points or local max or min. So critical points. For critical points, we need to set f prime of x equals 0. So that gives 2 cos 2x equals 0, which means cos 2x has to be 0. And then that means 2x is equal to pi over 2 or 3 pi over 2 or 5 pi over 2 or 7 pi over 2 or 9 pi over 2. And so on. So that means x is pi over 4 or 3 pi over 4 or 5 pi over 4 or 7 pi over 4. The next one will be 9 pi over 4. 9 pi over 4 is bigger than 2 pi. Remember, our domain is supposed to be 0 to 2 pi. And then if I continue to 9 pi over 2 as the value of 2x, x will be 9 pi over 4, which is still more than 2 pi. So I don't need to include this number because then x will be outside of the domain. All right, now let's look at the sign chart. So for sign chart, we need to include x values here. We start from 0. Then let's list these elements, the critical points. These are my critical points. Let's list them in the order. The smallest one is pi over 4. And then we have 3 pi over 4. And then we have 5 pi over 4. 7 pi over 4. And then the other endpoint of the domain is 2 pi. And then here, let's say f prime, and here f. So f prime becomes 0 at these points. And we can use a test point, for example, here. Let's say, for example, x equals pi over 8. And then f prime of pi over 8. The formula for f prime of x was 2 cos 2x. So this is going to be 2 cos pi over 4, which is positive. So positive here, negative, positive, negative, positive. And then f will be, if f prime is positive, f will be increasing. And then decreasing, increasing, decreasing, increasing. And then we will have local maximum here, right? If the function increases, then decreases, you will have a local maximum here. Here decreases, then increases. So local minimum here. Local max here. And local mean here. Okay, now are we ready to sketch the graph? We want the domain to be 0 to 2 pi. The function increases. Increases and decreases and increases and decreases. So this is pi over 4. And this one was 3 pi over 4. Five pi over 4. 7 pi over 4. And then 2 pi here. Okay, and these are the value. These values will be 1, the maximum, local max is 1, and local mean are -1, right? So this is local max. What is the point? The x value is size pi over 4. So the sign chart only gives you the x values, but when you want to sketch a graph, you need the points. Needing the points means needing the x values and also needing the y values. So how can we find the y values? We have to use the original function, the formula for the original function. What was the original function? F of x was sine 2x, right? If x value is pi over 4, then the y value will be sine, right? Sine 2 times pi over 4. Sine 2 times pi over 4 means sine pi over 2, which is 1. So this is pi over 4 and 1. Similarly, this one will be local mean. And the point is 3 pi over 4 and minus 1. And this one again, 5 pi over 4 and 1. And this one, 7 pi over 4 and minus 1. And that's it. This is the graph of the function that we were looking. Let me give you a remark here that the graph above, the graph of y equals sine 2x can be sketched, can be also sketched using graph transformations. If we use the graph transformations method, we can sketch the graph of sine 2x. How could we do that? So see sine x, we know the graph of sine x, how it looks like. So this is 0, this is pi, this is 2 pi. Now sine 2x, well, in pre-calculus, you saw this, that if you have, let's say, f of 2x, this is going to be horizontal compression by factor 2. 2 times f of x will be vertical stretch, but f of 2x will be horizontal compression. So the transformation on x-axis is counterintuitive. If you remember from pre-calculus, f of 2x, counterintuitive means it's opposite of what you would expect. F of 2x, because it's multiplying by 2, you would maybe initially expect that there could be stretch, but this is counterintuitive, opposite of what you would initially think. So it's horizontal compression, not stretch, it's horizontal compression by factor 2. So if we compress this by factor 2, then what do we get? We get something like this. Okay, so these are the local max of original function sine x. The blue one is sine x. This is what I call sine x. And then the black one, which is the horizontal compression of the original graph, is what I call sine 2x. Okay, so pi over 2 and 3 pi over 2 local max and min of original function, only 2 of them. But when you compress this, then we'll have more local max and min. We'll have 2 local max and min and at pi over 4 and 5 pi over 4, and 2 local min at 3 pi over 4 and 7 pi over 4. Okay, so my point is this graph could have been sketched in pre-calculus course using graph transformations, because we know that if you have the graph of f of x, in this case sine x, then the graph of f of 2x can be obtained by using horizontal compression by factor 2. All right, so let me give you some exercises. You can work on them later. For trigonometric functions, I did one example for you. Exercise, sketch the graph of following functions. The graphs of following functions. Part A, y equals sine x plus cos x. Part B, y equals x plus sine x. Let's say all of them on 0 to 2 pi. You can assume that the domain is 0 to 2 pi. Y equals sine x plus cos x, y equals x plus sine x. Part C, y equals x plus sine 2x. Part D, y equals cos squared x. So this is also one of the functions that can be sketched using the methods we learned in this course, using derivatives and finding local max and min. You can, again, of course, differentiate this function, find critical points, etc. But again, this function can be also done or can be sketched using the graph transformations, because cos squared x, we have a formula for it, right? Cos 2x was 2 cos squared x minus 1. So cos squared x, you can write it as 1 plus cos 2x divided by 2. So we can start from the graph of cos x, then cos 2x will be horizontal compression, like what we said. Then cos 2x divided by 2 will be vertical compression. If you have graph of f of x, 1/2 times f of x will be vertical compression by factor 2. And then you have to add this function with 1/2, because it's 1/2 plus this function. Adding with 1/2 means vertical shift. Vertical shift 1/2 unit upward. Okay, so it's going to be one transformation, horizontal compression, then vertical compression, and then vertical shift 1/2 unit upward. So there will be 3 transformations that you have to apply on the graph of sine cos x in order to get this function, if you want to use this method. But maybe it's easier for this function to do the method that we explained here, finding critical points, local max and min, etc. Yeah, so I just wanted to say that for this function, again, you have 2 options, similar to what we did in the previous example. All right, let's do some examples from, for example, exponential functions. Sketch the graph of y equals e to power minus x squared. E to power minus x squared. So solution, again, first we need to find the domain. For domain, we know that we have to look whether there is any restriction on x, because domain is not given. So we have to find the natural domain, meaning largest possible domain. And we have to see whether there is any x value, any values that x is not allowed to take. So here, we don't have any denominator, we don't have any square root, we don't have any logarithm. There is no restriction on x. X can take any value, basically. So domain basically is all real numbers, or minus infinity to infinity. Okay, domain is all real numbers, or minus infinity to infinity. And then we need to look at x and y intercept. So y intercept, we need to set x equals 0, then y will be e to power 0, which is 1. For x intercept, we need to set y equals 0, but y is an exponential function. Exponential functions can never be 0. They're always positive, right? So this has no solution. which means no x-intercept. No solution, so no x-intercept, because I can also mention that because the reason is exponential functions are always positive. Okay, and then we need to look at the asymptotes. Okay, we don't have any vertical asymptote because there is no value of, there is no x value that, or the that if x approaches to some number a, then the limit at a becomes infinity or minus infinity, because we have a function which is continuous everywhere, right? So there is no, so limit f of x as x approaches to a for any a would be f of a, and f of a for any a is a finite value. So there is no a that limit f of x as x approaches to a becomes infinity, because when we have a continuous function, a function that is continuous everywhere, limit f of x as x approaches to a is always f of a, and f of a is always a finite number. It cannot be infinity or minus infinity. So we don't have any vertical asymptote. And for horizontal asymptotes, for horizontal asymptote, we have to look at limit f of x as x approaches to infinity or minus infinity. Let's look at these limits. Limit f of x, x approaches to plus or minus infinity. This is equal to limit e to power minus x squared, x approaches to plus or minus infinity. And this is e to power minus infinity, right? Because there is a power 2 here. Therefore, whether x approaches to infinity or minus infinity, when it raised to power 2, the result will be infinity. Infinity to power 2 is infinity, minus infinity to power the whole to power 2 is also infinity. But there is also a minus in front. So this x squared will be infinity, whether x is infinity or minus infinity, but there is a minus in front. So the answer will be e to power minus infinity in any case. E to power minus infinity means 0. So limit f of x, x approaches to infinity and minus infinity is 0. So that means y equals 0 is our horizontal asymptote. Y equals 0 is our horizontal asymptote. Okay. If limit f of x, x approaches to infinity or minus infinity is a, then y equals a is horizontal asymptote. Please remember to say, because some people say 0 is horizontal asymptote. 0 is just a number. Horizontal asymptote must be a horizontal line. So when you say y equals a constant, then that's a horizontal line. All right. What about critical points and local max and mean? So for that purpose, we need to set f prime of x equals 0. F prime of x equals 0. What was f of x? E to power minus x squared. Derivative of this function, how can I calculate? See, e to power u. Derivative was u prime times e to power u. So e to power minus x squared derivative is minus x squared derivative times e to power minus x squared. So that equals 0. So that gives minus 2x e to power minus x squared equals 0. Again, e to power minus x squared is always non-zero. So that means 2x has to be 0, and that gives x equals 0. So x equals 0 is our critical point. Now let's look at the sign chart. And sign chart and basically first derivative test. And that will help us determine whether this critical point is local max or mean or neither. So these are the x values here, x values. And we have only one critical point here, which is 0. And then f prime here, and then f here. So f prime becomes 0 here. Now, before 0, let's use a test point. For example, we could use -1 test point. X equals -1. Then we get f prime of -1 equals -2 -1 e to the power -1. This is positive, positive, negative. And the function increasing here, decreasing here. Therefore, at 0, we have a local maximum. Okay, so are we ready to sketch the graph now? So the function at -infinity, remember y equals 0 is a horizontal asymptote at infinity and also -infinity. This limit is 0 whether x approaches to infinity or -infinity. So when we start at -infinity, we start with y equals 0. That's our horizontal asymptote. Then the function increases all the way until 0 and then decreases. And at 0, we have local maximum. Zero, remember, the x value of local maximum is given in the sign chart, but the y value, for the y value, we have to plug it into the original function, not derivative, the original function. Original function is e to the power minus x squared. If I plug x equals 0 there, what do I get? I get e to the power minus 0, which is 1. So this is 0 and 1. So this is my local max. So the function increases. See, starts with, it seems the screen is freezed. Starts with y equals 0 at -infinity as a horizontal asymptote, and then increases all the way to 0, x equals 0, where we have, it has a local maximum, then it decreases and again approaches to 0 as x goes to infinity. So basically this is a bell-shaped curve, okay? So let me give a remark here. So the solution is complete here. We sketch the graph of this function. This is a graph of y equals e to the power minus x squared. E to the power minus x squared. Remark. The graph above, or the function above, with a bell-shaped curve has a lot of applications. In probability theory. If you take a probability theory course, for example, Math 206, you will see that, you know, in many scenarios, in many applications of probability or in random processes, you need a function that determines density of distribution for your probability. So in other words, it determines basically area under the curve of that function will give you the probability, or the integral or area under the curve of the function will give you the probability between any 2 points. So normally, if you are around average, it's more probable that you are in that area. For example, think about the midterm grades. Midterm grades. If let's say the average is 70%, then it's more probable that a student, the grade of a student is between 65% to 75%, compared to 85% to 95%. If the average is 70, then it's more probable that the grades of students are around that point, around that mark. And less probable as you get farther and farther from the average, then the probability becomes less and less. So if the average is 70, 65 to 75 more probable compared to 55 to 65, and 55 to 65 is more probable compared to 45 to 55, right? Similarly, 45 to 55 more probable compared to 35 to 45, and so on. So as you get farther and farther from average, it's going to be less and less probable that you have grades there. So we need a curve that has this property, that has a maximum at the average. And as you get farther and farther from the average from either side, then it becomes less and less. The values of the function becomes less and less, because when the values of the function get less and less, the probabilities will become less and less as well, because you will see in Math 206 that the probabilities will be the area under this curve. So if the curve has smaller values, area under the curve will be also smaller. So we need a bell-shaped curve function that has a maximum at some point, and then decreases on both sides. And this is exactly the function that we can expect in that context. But here the maximum is at 0, but you may tell me that, okay, when we look at the midterm grades, the average cannot be 0. Average could be 60% or 50%, depending on the course, or 40%. Well, that's true, but we can have a shift, right? So the average of this function, the maximum of this function is at 0, but if I shift it, let's say 10 units towards right, then the maximum becomes at 10. Or let's say if I shift it 70 units, then the maximum becomes at 70. So I can still use this function, I just need to shift it. You'll see all these details in a probability theory course. I just want to say here why this function is very important, especially in probability theory. Okay, another important feature of this function, because there could be some other functions that have this property that they have some maximum at some point and then they decrease from both sides. But this function has other important features as well. For example, this function is differentiable because it's smooth. See, there is no sharp point, right? So it's smooth and it's differentiable. Differentiability is important in many calculations, right? So that's another nice thing about this function. Another nice thing about this function, remember I told you that the probability will be given by area under the curve. So you will see in Math 206 that the total probability always has to be 1. In percentage means 100%, but without percent means total probability has to be 1, which means the total area under the curve has to be 1. Well, if the total area under this curve is not exactly 1, but it's a finite number. That's a good news. Because if it was infinite, then we cannot make it 1. It's already infinity. But if it's a finite number, for example, let's say if it's 6 total area, it's not 6, but let's say if it's 6, if it was 6, then I could divide my function by 6, scale it by basically 1 over 6 times the function, and then that new function will have area 1. So after scaling, because this area is finite, after scaling, I will have a function where the total area becomes 1, which will represent the total probability. So see, this function has many amazing features, all of them suitable for probability theory. Okay, I just told you some ideas so that you get familiar with this function, and when you take that course Math 2-6, you already have some idea about what you need, what type of function you need in that course. All right, so let me give you some exercises for exponential functions. You can try to sketch them later. Exercise, sketch the graphs of following functions. Part A, f of x equals e to power 2x. Part B, f of x equals, let's say e to power x if x is positive. And e to power, or let's say e to power minus x if x is positive, e to power x if x is negative. Seems the screen is freezed. Okay. E to power minus x if x positive, e to power x if x negative. You will see this function also has the feature that has a maximum at 0 and it decreases from both sides, but still is not as nice as the function that I said, because you'll see, you can check that it's not differentiable at 0. That's one thing. You can check that. Another thing is area under the curve, or integral of that function. Well, for integral, you still don't have the tools. You have to wait until next semester to see whether, after you learn about integrals, then you can check whether the area or integral of this function, is it infinity or not? Because remember, we said we prefer something finite so that we can scale it and make it 1 in the context of probability theory. But those are the issues or concerns that you can think about them later. But for now, you just want to sketch the graph of the function. And of course, you need to determine, for example, critical points, local max and min, asymptotes, etc. Okay. And the next part, part C, f of x equals x times e to x, x times e to power x. So please try to sketch these functions. So this was an example for exponential functions. Let's also do one example for logarithmic functions. An example, sketch the graph of y equals f of x equals ln x over x. Solution, again, first we need to find the domain. Well, for domain, we have to look at the restrictions on x. Which restrictions do we have on x? Well, when we have a logarithm here, the argument for logarithm has to be a positive number, right? So we have ln x, and therefore x has to be positive. And we also have denominator. So x has to be positive, denominator has to be not equal to 0. So that means x not equal to 0. So these two together, so this one and this one, right? But if x is bigger than 0, well, it's automatically not equal to 0, right? You want x to be bigger than 0 and x to be not equal to 0. Well, if x is bigger than 0, you will automatically have this one. So we just need to require x to be bigger than 0. In other words, we have to take the intersection. And intersection is x bigger than 0. So domain is 0 to infinity. Then we need to look at x and y intercepts. Well, x equals 0 is not, for y-intercept, we need to set x equals 0. But x equals 0 is not in domain, so there is no y-intercept. Domain is open interval 0 to infinity. X equals 0 is not there, so we don't have any y-intercept. And for x-intercept, we need to set y equals 0. So that gives ln x over x equals 0. So if a fraction is equal to 0, then that means numerator has to be 0. So that gives ln x has to be 0, and that gives x equals 1. And then we need to find a critical, or let me find asymptotes first. Asymptotes. Well, asymptotes, for vertical asymptotes, we know that if you have a logarithm, the zero of argument of logarithm, expression in front of logarithm, the zeros of that could be potentially vertical asymptotes. Also, if you have denominator, zeros of denominator could be potentially vertical asymptotes, but of course we need to check. So potential vertical asymptotes, and because we have ln x, so x had the expression inside logarithm here is x itself. You have to put the expression in front of logarithm equals 0, but the expression is x itself, so x equals 0. And denominator equals 0. But denominator is also x. So it's just coincidental here that expression in front of logarithm is x, denominator is also x. So the values that we get from these two are the same. So just one, we have only one potential vertical asymptote. But like I said, this is just very coincidental. We could have ln x minus 1, for example, here, and denominator could be x or something else. In that case, the values obtained from these two equations would be different. And therefore, in that case, I would have, for example, 2. If I get one value here and one value here, I would have 2 potential vertical asymptotes. But here, the values are the same. So we have one potential vertical asymptote. Which is x equals 0. And then we need to check the limit. In order to verify whether it's actually a vertical asymptote or is it just a potential vertical asymptote, we need to see whether the limit as x approaches to this number, is it infinity or minus infinity or not. So limit ln x over x as x approaches to 0 from right. Because a domain is 0 to infinity, so x cannot approach to 0 from left. It can approach to 0 from right, though. So this limit, right limit, will be limit ln x times 1 over x as x approaches to 0 plus. So then this is ln 0 plus times 1 over 0 plus. ln 0 plus, if you think about the graph of ln x, which looks like this, right? If x is a little bit bigger than 0, y value will be minus infinity. So this will be minus infinity. And 1 over 0 plus is positive infinity. Minus infinity times positive infinity is minus infinity. So we do have a vertical asymptote at x equals 0 because the limit was minus infinity. Now for horizontal asymptote, we need to let x go to infinity or minus infinity. But here domain is 0 to infinity, so x cannot go to minus infinity, but x can go to infinity instead. So if x goes to infinity, limit f of x as x approaches to infinity will be limit ln x over x as x approaches to infinity. So this is basically infinity over infinity. And infinity over infinity, we can use L'Hopital's rule, right? So indeterminate form, that we can use L'Hopital form to simplify it. So then if you use L'Hopital rule, we get limit derivative of top over derivative of bottom. Derivative of top is 1 over x, derivative of bottom is 1, x goes to infinity, and then this is limit 1 over x, x goes to infinity, 1 over infinity, and that's 0. So that means y equals 0 is our horizontal asymptote, because limit f of x as x approaches to infinity is 0. So that means y equals 0 is our horizontal asymptote. Okay, then we have to find the critical points and local max and mean. And for that, we need to set f prime of x equals 0. Well, f of x, the formula for f of x was ln x over x. Derivative of this function, for derivative of this function, of course, we have to use the quotient rule. Quotient rule says u prime v, derivative of u over v is u prime v minus u v prime divided by v squared. So here it will be ln x derivative times x minus x derivative times ln x divided by x squared equals 0. So then derivative of ln x is 1 over x, 1 over x times x minus derivative of x is 1, 1 times ln x divided by x squared equals 0. So that gives 1 minus ln x divided by x squared equals 0. Now, if a fraction equals 0, then top equals 0. This fraction here is 0. So that means top has to be 0. Top is 1 minus ln x. So 1 minus ln x equals 0. And that gives ln x equals 1. ln x equals 1 means x equals e, right? ln x means logarithm in base e. So logarithm x in base e equals 1. That means x is equal to e to power 1, which is e. But we have only one critical point here. Now let's use the first derivative test and use the sign chart to find out whether this is local max or mean or neither. So the sign chart here, are the x values start from 0, and then we have e, and then we have infinity. So then we need to write f prime here, and then f here. F prime becomes 0 at e. And then before e, let's use a test point. I could use, for example, x equals 1. E is 2.7 something, right? So I could use x equals 1, let's say, x equals 1. Then f prime of 1 will be 1 minus, what was f prime of x? 1 minus ln x divided by x squared. So 1 minus ln 1 divided by 1 squared. ln 1 is 0. 1 minus 0 is 1, divided by 1 is 1, which is positive. So positive here, negative here. Okay. And here, therefore, f will be increasing and decreasing, and local max here. Increasing, then decreasing, so local max. And we are ready to sketch the graph of the function. And please remember, x equals 0 was a vertical asymptote, and the right limit was minus infinity. Right? X equals 0 vertical asymptote, right limit was minus infinity. So here's we start from minus infinity, the function increases, local max here, and then decreases. So let's sketch the graph of function. The domain is 0 to infinity, so we have graph only on the right side of x-axis. We start right after 0. The domain is open interval 0 to infinity. So we need to start right after 0. Right after 0, the limit is minus infinity. We start from here, and then we go up and then we decrease. So see, the function increases all the way until this point. This point is E, our local max. Local max. Remember, local max, that means the X values are given by the sign chart. The Y values are given by plugging into the original function. Original function was ln X over X. So ln E over E. That will be the Y value of the point for local max. Ln E over E, ln E is 1. So this is E and 1 over E. This point E, so the Y value is 1 over E. So right after 0, the function starts at -infinity, increases all the way to this point, local max, then decreases. And remember that y equals 0 was horizontal asymptote. So decreases, the function decreases, and as x goes to infinity, y value approaches 0 because y equals 0 is a horizontal asymptote. And it's the limit as x approaches to infinity. We had it here. Okay, so decreasing here, decreasing, and as x approaches to infinity, y approaches to 0. And we also saw that we have one x-intercept at 1. So this point is 1. And we saw that we have no y-intercept. We had only one x-intercept. Okay, guys, so this is an example for logarithmic function. If you want more practice, exercise, sketch the graph of following functions. So we did for ln x over x. You can try x times ln x. You can also try f of x equals x squared times ln x. And part C, f of x equals ln x squared plus 1. Okay, so try to sketch these functions. And of course, you need to find local max and mean and critical points and asymptotes as well in order to sketch the graphs. Okay.